And the recording is going. And okay, so last time we were talking about path independence. And recall path independence is a property of a vector field. Vector field is path independent if, just like it says, if the value of the line integral is mostly independent of the path. Right, with the one little requirement that the starting point and the ending point have to be set and fixed for you to have that flexibility. Okay, all right. So we're going to see today some conceptual uses for path independence that I think are really nice, and there's more conceptual uses than that alone. By the way, there are some conceptual applications of path independence to physics. And if you're curious about that sort of thing, it'd be a great office hours question to come and talk about. It'd take about 5 minutes or something to talk through that. I had some nice ideas, though. So on a computational level, though, there's some a case could be made that you don't really need path independence as follows. If, in fact, a vector field is path independent, well, that means that it's a gradient. Right? We talked about that last time. And if it's a gradient, then that means that you can use the fundamental theorem of line integrals, which we've already seen is awesome for computing line integrals. Right? So why do we really need this idea of path independence, at least from a computational standpoint? If in fact any case in which you could use path independence, you could also use what we already know is fantastic. Right? So path independent from a computational standpoint is a nice tool that we already own in some, like we already own a better tool. So why would we need it? Still, I want to point out there are some situations where you can use path independence, and here is one. So here's a vector field that I'm going to assert is path independent. Now, how I know that, we'll see soon. For the moment, I'm just going to assert it with no justification. And that said, for this path-independent vector field, let's compute the line integral on this curve, namely the top half of the unit circle oriented clockwise, like so. So how am I going to compute then this line integral? Okay, well, here's how we're going to use that path independence. Because it is path independent, as long as I fix the starting point and fix the ending point, I can take this curve, my existing curve, and I can just pretty much throw it away. I can say, you know what, I don't even like that curve. I don't like the fact that if I were to parameterize this curve, it would have sines and cosines or square roots, even worse. And I don't really like that, so I'm going to use my path independence and say, okay, how about this curve instead? Right? What an outrageous thing to do in a question. I don't like your question. I'm going to change the question. Right? Seems unfair. But because of path independence, I can take the question I was asked to compute the line integral over the blue curve and instead say, I'm going to compute the line integral over the green curve. Again, because it's path independent, you certainly can't do this for most vector fields. But here I'm going to replace the blue curve with the green curve and say just phooey on the blue curve, and I'm going to compute this line integral then instead, parameterizing this green curve much easier. Super easy. No trig, no square roots. Nothing hard at all. And I have a much easier integral that results. A couple of things to say about that computation, but before we go on to those details, is everybody happy with how I just changed curves? Okay. Yes?
So can we also use FTLI in this?
Yes, absolutely. You could. I'm just showing you how you would use path independence if you were so inclined. But you're absolutely right. So let me point this. Let me flesh out those details a little bit. Because it's path independent, I know it's a gradient, and so I know that there is an anti-gradient, right? That I could find, and I could try to find that anti-gradient. And which as of yet, I still haven't told you all how to do, right? Other than guess and check. But yeah, absolutely, there is an anti-gradient. You could use that anti-gradient No problem. Yep. All right. Here's the details of how you would do it this way if you were so inclined. Recall that I can expand my vector field, and I can expand dx, right? And a couple of nice things I can do. For one thing, this displacement vector, this dx vector along my current curve, notice it's all horizontal. Y doesn't change. And by virtue of y not changing, dy is 0. That's nice, right? It's a neat little hack you can use for yourself there. How about that? That's nice. And here's the other thing, though. By virtue of the fact that, again, I am on this green curve, that green curve, you will notice y is also always 0. And that means I can take the fact that y is equal to 0, plug that in for that y right there, and not only is dy 0, but the first component of the vector field also 0, flat 0, for the purposes of what I'm doing. Right, so with these two observations together, f dot dx turns into that calculation right there, which is 0 at a glance, and we're done here. This integral is 0. So path independence combined with a couple of, oh, hey, check this out, and we're done with kind of all, I'm going to say in some sense, no real effort, right? I didn't have to, technically I had to parameterize a straight line, right? But I didn't have to deal with trig or square roots or take any antiderivatives. It just kind of falls apart. Everybody on board? Okay. Nice method. All right. So, okay, how did I know that this was path independent? Rhetorical question. Here's where that came from. It came from what I'm going to call this local test, and I'll explain what I mean by that in a second. Well, I'll just do it right now. The local test is that you can decide on the question of whether a function is a gradient, a vector field is a gradient, by computing Green's operator and seeing if you get 0. Now, why does that work? Where does this come from? And there's a couple different ways you can say this. I'm going to show you what I think is the most kind of convenient algebraic sort of version of this. To start off, if you have a gradient, we already know that it's path independent, and vice versa. And furthermore, path independent, we know we can rewrite with this kind of alternative formulation about closed line intervals. That's all from last time. So I'm going to take that as a starting point. Next, closed line integrals. Well, that means, if you think about it, line integral around a curve that starts and ends at the same point, that if it's a closed curve, it's also a boundary, and integrals on boundaries can be computed as double integrals of Green's operator. Right? Does everybody remember? So this is Green's theorem right here, which I highlighted in green. Right? So saying that the closed line integrals are all 0 is equivalent to saying that these double integrals are all 0. How are we doing there? Everybody with me so far? Okay. All right, but this is a weird statement, though, if you look at it. This says that for every two-dimensional region, not just some two-dimensional region, every two-dimensional region, this double integral is always 0, no matter what region you pick. How could that be? What is the only function, what is the only integrand that has that you can think of that has this property? That every double integral over it, no matter what region you pick, double integrals, always 0. The only such case is if that integrand itself is 0. that make sense to everybody? So it's a neat little kind of connect the dots of sort of different ideas, but being a gradient means path independent, means closed line integrals are 0, means double integrals of Green's operator are always 0, means Green's operator just has to be 0. So, like I say, nice little connect the dots of ideas there. Now here's a kind of a streamlined version of this. It's ultimately the same idea, but just kind of, with the, let's see how to say this, without the equations, right? Less equations, as follows. If you remember, what is a closed line integral? Closed line integral, that's circulation. Right? We've talked about circulation previously. So you could view this whole argument as saying, if circulations are always 0, shouldn't it mean then that circulation density is 0? Right, now that rolls off the tongue pretty nicely. Circulation 0, circulation density must be 0. Let's take a mass analog of this. If everywhere you look there's no mass, well, there's also no mass density. Right? There's no mass. There's no mass at all anywhere. Well, then there's no density, mass density anywhere. This is the analogous thing about circulation instead of mass. What do you think? Everybody all right with that? It's just a point of view, right? So, like I say, ultimately the same argument, but just kind of a streamlined version of it. Okay, so again, powerful tool. This is a local test. I call this a local test because this thing that you compute is computed one point at a time. Right? You give me a vector field, I compute Green's operator. It's a formula. I can compute that myopically. I can just look at one little point and not look at what's going on over here. I can just focus on one point at a time to compute Green's operator. And then I just have to check that it's 0. Everywhere. What's cool about that is that the conclusion you get is not really a local thing, right? Saying that there is an anti-gradient, there has to be a function defined globally. It has to be defined everywhere, and everywhere have the feature that its gradient gives you the same value as the vector field. Right? So this is a non-local property that connects to this local property. Okay. All right. Let's talk a little bit more about this local test. Quick reminder, what is Green's operator? Green's operator is what I like to call circulation density. It's a measure of how much the vector field is kind of rotating, again, if you will. Right. So imagine fluid flowing along. A vector field represents the flow of a fluid, and there's, it's the surface maybe of a little creek or something, the water flowing along. And if you drop a leaf into there, that leaf moves, but that leaf also kind of turns. A leaf will have a rotation to it because the fluid is rotating. And Green's operator is a measure of how much the fluid is rotating. So, if that fluid, if the Green's operator is 0, that means that there is no rotational aspect to the fluid, and thus the term irrotational. It'd be tempting to call it non-rotational, right? But they say irrotational. So I think this is a nice single word to describe the property of Green's operator being 0, and in common use. How are we doing? Is everybody all right with that? And so now I want to let's take stock for a moment and talk about different ways that we have of describing these vector fields. Remember, we were talking about vector fields that are gradients, right? So these vector fields are gradients. These vector fields, same vector fields now, also path independent. And we see now, same vector fields also irrotational. Right? So this is three separate terms that are all describing the same exact vector fields. And again, quick reminder, there's some formalities I'm sweeping under the rug. I don't want to deal with regularity conditions, so I'm assuming everything in sight is continuously differentiable. So let's not deal with the ugly details there. So we have three separate terms. Why do we have three separate terms talking about the exact same vector fields? Well, these are talking about different features of the exact same vector fields, right? So the feature of being a gradient of a function, that is a different statement that can be used in different ways than this statement of being path independent. It's a different yes, it's the same vector fields, but it is a different feature that they have. And likewise, the statement of Green's operator being 0 is a different statement. And they're connected. There's ways to, this argument here shows connections between all those ideas, but they are all different ideas. Okay, so here's the arguably funny thing. There is a fourth term that again describes all of these same vector fields. And that word, you've seen it before in the notes. It's conservative. There are some physics reasons why gradient fields, aka path independent fields, aka irrotational fields, there's some physics reasons why one might use the term conservative. But I kind of feel like we have enough of those terms at this point. And so I tend to personally not use that term so much because I think these are better. And if you look at the definition of conservative, depending on what book you look at, they'll define conservative as being, well, it's a vector field that's a gradient, perhaps. To which I ask, well, then why don't we just call it a gradient? Why do we invent a new term for it, right? What additional feature of these vector fields does the word conservative point to? And likewise, it could be defined as path independent. It could be defined as irrotational. So, anyway, I tend not to use the word conservative very much. Heads up, it's very common though. Right? So I want y'all to know that, yeah, it's out there. It gets used a lot. You're going to hear me say gradient or path independent or irrotational, depending on which of these features I'm interested in talking about at the moment. But elsewhere, you're going to hear the word conservative, and you need to remember that when you hear conservative, you get to think, it's a gradient, it's path independent, and it's irrotational. Okay. All right. Now, let's see here. Another thing to say. This local test, as I have written here, is exclusive to 2 dimensions. Has to be exclusive to 2 dimensions because it comes from Green's theorem, which of course is exclusive to 2 dimensions. So, is there a local test in 3 dimensions? Why, yes, there is. Here it is. This is the local test in 3 dimensions. And you want to know if something's a gradient? Well, it's a gradient if and only if curl is 0. So here we have curl playing a role highly, highly analogous to the role that Green's operator plays in 2 dimensions. Okay. Now, how do I know that this statement here is true? Again, regularity issues aside, let's not worry about discontinuities and singularities and stuff. There is a great argument for this, and it looks just like the argument we just gave for Green's theorem. The only problem is it uses a theorem that we haven't covered yet, so I can't show you that argument. But it's the same conclusion, and it's the same strategy. Again, we're just missing one of the pieces needed to connect those dots, and we'll have that piece in a couple of weeks, and I will revisit this at that time. Okay. For the moment, we're just going to use it. Here's how we use it in practice. Here you go, 3-dimensional vector field. Right? Vector field with 3 components. So this is in R3. Is this a gradient? Want to know if it's a gradient? Fine. We resolve that by computing the curl and seeing if it's 0. So we start off in that process. We compute the curl here. Remember, there's various partial derivatives to be computed to compute the curl. And here's the first component. And then we could go on. The thing is, we don't really need to. Technically, you'll notice up here, I don't actually need to know the curl. All I need to know is the curl equal to 0? And I have already seen here, this first component clearly not 0. Right? It's just, these terms don't cancel. That means there's some values of x, y, and z where this is not 0. And if one of the coordinates is not 0, the vector is not 0. So curl not 0. And so this is not a gradient. Everybody see how that works? Now, if it had been 0, there's a temptation to say, oh, I got 0 for my first component. I don't need to go any further. Yes, you do. If you get 0 for the first component, you might get not 0 for the second component, or maybe you get not 0 for the third. So it's not... This little hack that I did here of stopping after the first coordinate only works because it's not 0. Okay. All right. Moving along. Let's see a two-dimensional example. Here's a two-dimensional vector field. Is this a gradient? We compute Green's operator. A couple of partial derivatives, easy to do. Green's operator is 2. Which is not 0, and so again, no, this is not a gradient. Everybody all right? Okay. I'm going to give you a different point of view now on this example. Let's notice that this vector field, I can draw a picture of it. There it is. Is this a gradient? Well, let's remind ourselves... if it's a gradient, gradients point uphill. Wait a second. Could these vectors all be pointing uphill? Well, if they were pointing uphill, then as I walk directly uphill, right? You can see what's about to happen here. I keep going higher and higher and higher, and yet somehow I manage to get right back exactly where I had been. Right? According to the gradient, my altitude has increased by some positive amount. But according to the fact that I've returned to exactly the same place, my altitude hasn't changed at all. This is a contradiction. This is Escher-Stairs nonsense. It's just not possible. Right? So one way to say this, I mean, just for rolling off the tongue purposes, is uphill can't circulate. Right? You can't keep going uphill, 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 and coming right back to where you were. It just doesn't work. Pausing. Questions? That all make sense? Okay. Alrighty. Okay. So, this, what I call a strategic diagram for R2. I want to first let you know where this came from. I've already made some allusions to how there's a much more sort of abstract and sophisticated machinery that one can build up and take a very hardcore take on all of this stuff. And we're not going to do that in this course. That's not what Math 219 is about. If you're curious what that looks like, check out Chapter 8 of our textbook. And you can see what that stuff all looks like. It's very abstract, and it's very cool. It's very powerful. It's very powerful stuff. But it's not what we're going to do in Math 219. So what I have here is I took some of the important machinery from all of that more sophisticated stuff, and I kind of boiled down all of the rigor and all the formalities and all the abstraction, and just kind of what's left over here is just a bare bones kind of so I call this a diagram, strategic diagram. But what this does is it shows certain kinds of connections that make the formality much easier to do. And drawing this diagram in this way then will have certain advantages. Even though we're not going to use the formality, this is an ultimately natural and just well-advised way to kind of organize the ideas on the page. So let me walk you through how this what we've got going on here. Recall, gradient of a function gives you a vector field, right? And recall, Green's operator of a vector field gives you a function, a real valued function. And we've talked about this idea previously of exactness. I claim that this sequence here is exact. Recall, exact means this business about lifetimes being 2, right? And so, for example, if you have a function, if you take the gradient and you get a vector field that is non-zero, well, that was its lifetime of 2. And so if you apply Green's operator, you have to get 0. Right, so Green's operator of a gradient is always 0. It's easily confirmed. The other thing is, if you have a vector field for which Green's operator is 0, well, this could not have been its whole lifetime. That's only a lifetime of 1. Right? So this vector field must be the gradient of some function. Right? Okay. So you can, in fact, this is really just kind of a diagrammatic representation of what we saw up here. Being a gradient means Green's operator is 0. Okay. Here's the other thing, though. If you have a 2-dimensional region and you take its boundary, that's a curve. And then furthermore, if you have a curve and you take the boundary of a curve, you get a pair of points. Unless it's a closed curve, the 2 points are, the same point. There is effectively then no boundary. Okay. Nevertheless, generically, curves, boundaries are points in some sense, possibly 0. Okay. All right. So, surprising fact, this is approximately an exact sequence also. And we've not talked about this before. This is just a neat fact of geometry. This is just how geometry works. Kind of interesting, but if you have a 2-dimensional region and you look at its boundary curve, that boundary curve cannot have endpoints. Right? So said differently, its boundary is going to be 0. Does that make sense? I mean, it's just geometrically, right? Can you think of a 2-dimensional region whose boundary curve ends? Right? You just can't. It's no such thing. Okay. And then likewise, if you have a curve whose boundary is 0, right? Well, that means that the curve is a closed curve. That means that it must be the boundary of a region. It encloses a region. And then along those same lines, if you have a curve, let's say something that looks like that maybe, if you have a curve whose boundary is not 0, maybe it's a pair of points like this, right? Curve, boundary is a pair of points. Well, then here's its lifetime of 2. That means it can't be the boundary of a 2-dimensional region. If it were, that would be a lifetime of 3. Not possible. Also, geometrically, I mean, again, if a curve has endpoints, it didn't close up, it can't bound a region. Okay. All right. Okay, so neat facts. Let's see here. Let's talk about our boundary theorems, our accumulation theorems, however you want to say them. Let's see here. So here's the fundamental theorem of line integrals. And I'm going to give you a point of view here on the fundamental theorem of line integrals as it relates to this diagram. This says we're doing a line integral over a curve of specifically a gradient vector field. Right? On the other side over here, we're looking at f of b minus f of a. That's an evaluation at certain points, specifically boundary points of of a function, but specifically the function whose gradient you were looking at over here, and these two things are the same. Right? So another way to say this is that if you have a function and you compute its gradient, if you have a curve and you compute its boundary, then the evaluation of the function on those boundary points and the evaluation of the vector field over that curve as a line integral, same. Okay. Now, what I think is really interesting, and I think unexpected, is that even though Green's theorem, totally different theorem, right? Green's theorem is not about curves with boundary points. It's not about gradients. It's not about change, right? And yet, if you look at what Green's theorem says that if you have a vector field and you look at Green's operator of it, if you have a two-dimensional region and you look at its boundary curve, then this circulation, right, namely around the boundary curve of the original vector field, and this double integral over the original region of Green's operator, same. So the pattern, right, the diagrammatic pattern of Green's theorem looks exactly the same as the diagrammatic pattern of the fundamental theorem of line integrals. Isn't that weird? Right? Geometrically, they look totally different. This is about two-dimensional regions. There's nothing two-dimensional in sight for the fundamental theorem of line integrals. Right? This is fundamental theorem of line integrals is about gradients. There's no gradient anywhere in this discussion of Green's theorem. They're totally different, but they're structurally the same. Is everybody on board? Does that all make sense? Okay. All right. Let's talk about the special vector fields. We just got through talking about our special vector fields. By the way, keep in mind, this is all in R2. Two-dimensional only. There's a three-dimensional version of this diagram. We'll get to that in Chapter 7. We don't have all the participant. There's big theorems in Chapter 7 that we haven't developed yet, and types of integrals that we haven't developed yet. We got a long way to go before we can do the three-dimensional version of this. So this is all two-dimensional. But the special vector fields that we've talked about gradients. Right? A gradient is a vector field that is the gradient of something, thus the term, right? You can call it conservative if you like that. Let's see here. Path independent. I like to represent path independence like this. Path independent, if you have two curves that have identical boundary points, right? They start at the same point, they end at the same point, right? Then you also get the same value of the line integral. So that's how I like to draw path independence. And then here's how I like to draw irrotational. Keep in mind, irrotational means that Green's operator is 0. So so we know that these in what I have in yellow, certain vector fields. Now this is just the special vector fields are those that have all any one of and therefore all three of these property: green, orange, and blue. Okay. All right. Recall further. How do I know that these are the same? What is it that allowed me to connect gradients to path independence? Well, it was the fundamental theorem of line integrals that connected those two ideas. And if you look back through the notes, when we made that connection, the fundamental theorem of line integrals was the thing that did it. And what was the thing that connected path independence and irrotationality? That was Green's theorem, and that's what we did just earlier today. Okay. All right. So everything that I have on the screen here for 2 dimensions, there is a 3-dimensional version of all of this. The diagram is going to look a lot like this, except there's going to be, of course, not just 0-dimensional points, 1-dimensional curves, 2-dimensional regions. There will also then be 3-dimensional solids there will be sort of, in some sense, extra space, extra columns on this diagram. And this pattern that we see here will show up in exactly this way in multiple places on that three-dimensional diagram. So that's just a little bit of foreshadowing. So what we're doing here is we're establishing some groundwork for future discussion in Chapter 7. Okay. All right. Last thing to point out, just from a, but how do I compute stuff point of view? If you want to compute a line integral, I claim the diagram actually helps you a lot with this. If you want to compute a line integral, let's see, I better clean this up a little bit. Here we go. If you want to compute a line integral, well, here's a couple of line integrals that one could compute, possibly. And so let's take them one at a time. Can I use this here? Can I use the fundamental theorem of line integrals to be able to compute the line integral that I want? Well, what would I need in order for that to be the case? I would need to, whatever curve I have, that curve, I would need to look at the boundary points. Sure, fine, no problem. Just look at the boundary points. Not an issue. The problem is the integrand. That integrand would have to be a gradient of something. And that's less obvious, right? You can't just say, just find the antigradient. Sometimes there is no antigradient. Right, so that's the question. And how do I resolve this question? I resolve this question, is this a gradient, by computing Green's operator and seeing if I get 0. Right? So notice the diagram kind of suggests all this to us. Right? We're looking at our vector field, and it says right here, apparently I need that to be a gradient to use the theorem. And apparently I need to apply Green's operator to check that. All right. Okay. Now, on the other hand, maybe, in my hope to compute this integral, maybe I could use Green's theorem. Maybe I should be looking over on the right side of this diagram. Well, to do that, I would have to take whatever my vector field is. I would have to compute Green's operator. Sure, no problem. You can always, it's made out of partial derivatives. Just follow the formula, right? Computing Green's operator, that's not a sticky wicket. No problem at all. The question, the problem, is this curve. It says right here, that curve needs to be a boundary of a two-dimensional region. Said differently, I would need to be able to take that curve and determine from the curve what I like to call the anti-boundary. Right? Boundary takes a region, gives you a curve. If you're starting with the curve and you want to know, is there a thing whose boundary, that region, right? You're moving backwards through the boundary arrow, and so I call it anti-boundary. Does that make sense to everybody? In the same way that I call this an anti-gradient. Okay. All right. And how do we decide if we can do this? How do we decide if there is or is not an anti-boundary? Well, the diagram suggests look at the endpoints. Right? You got a curve. Look at those endpoints. If the endpoints are the same point, if the start and the end are the same point, then that is a closed curve, and that closed curve is a boundary of a region, right? And if it's not, if your boundary points, let's see here, if you have a curve, and if the boundary points are not the same, then your boundary is non-zero, right? You got two boundary points. That's non-zero boundary. You can see from this picture, it's not the boundary of a region. Now, in practice, most of the time, I mean, day in and day out, do you have to actually play this business about the exactness of the boundary sequence? No, in practice, it's usually pretty obvious by inspection. You just look at your picture and see if it's a boundary or not a boundary. I just like to point out that the exactness you can view this as another example of how exactness could be useful. Okay. All right. Okay, so I hope you'll find this diagram useful. I certainly do. Everything that I understand about vector calculus and Green's theorem and the connections and relationships and interpretations between them, in my mind, I mean, this is the way to kind of think about all that and to put the idea. This is how I organize those ideas in my mind, and I think that's very valuable. And I hope you'll consider doing the same thing there. All right. Last thing we're going to do in chapter 6 is finally get around to talk about how to find antigradients. Right. So there have been a couple of examples we've done in the past. When we first wrote down the fundamental theorem of line integrals, I just produced out of thin air with no justification. I just produced an antigradient. And no suggestion of how I did it. Right? So here's the method. Here's how I did it. It's not really that big a deal. It goes like this. Keep in mind that gradients look like this. If you want your vector field to be a gradient, that means that P, Q, and R have to be these partials. And if you think about it, that means that P has to be the x partial of f, which, if you think about it, means that f has to be the x antipartial of p. And not much happened there, right? I'm just observing that these two statements are the same thing, just kind of said backwards in some sense. Is everybody with me so far? Everybody? So if the x partial of f is p, take an x antipartial of both sides, f must be the x antipartial of p. Okay. All right. Likewise for the other coordinates, right? Q got to be the y partial. Well, that means that f is the y antipartial of q. And likewise for the third. Now, here's the catch. Here's the little tricky part. There's actually a bunch of x antipartials of p. You all remember from single variable calculus, whenever you do an antiderivative, you have this instinctive reaction. You always have to say plus c, because any constant, you put any constant in there, still an antiderivative, because when you take the derivative of a constant, you get 0, right? So to this antipartial, I need to add constant. Well, wait a second. What I really need to add, I need to add anything whose x partial is 0. Now, if you think about it, you want the x partial to be 0, all that means is this just needs to be an expression that doesn't have any x's in it. Right? And so that's why it's not just a constant. This is what we call a partial constant. This is any function of y and z. And then altogether, this is the general antipartial, the general x antipartial of that function p. And any whatever nonsense function of y and z you put in there, when you take the x partial, it just disappears, and this equation still works fine. That makes sense to everybody? Okay. So likewise for these others, for the y antipartial, you can add any partial constant function of x and z. And for z, any partial constant function of x and y. Okay, so the game then, the way this process works is, you observe that this being a gradient is synonymous with all three of these expressions here being equal to that same function f. And so the game is you write down these three lines, and you just try to figure out what do these partial constant functions have to be to make these all equal to each other. That's it. Let's see one. Okay, here's a vector field. This is a three-dimensional vector field, of course you notice. I compute the curl. It is 0. So we do expect that there should be an anti-gradient. By the way, I do think this is a useful point to keep in mind. You know, I try to avoid, all else being equal, try to avoid going off on mathematical wild goose chases. Right? Don't try to find something that doesn't exist. Right? So it's a nice move to, if you're looking for an anti-gradient, go ahead and take the curl first. Just check that you get 0. Right? If you don't get 0, game over. Don't waste your time. Right? So yeah, here we do get 0. So there should be an anti-gradient, and so we proceed confident we're not wasting our own time here. I got to take the x antipartial of the first coordinate, the y antipartial of the second coordinate, the z antipartial of the third coordinate. That's easy algebra to do. You get these terms here. And are these functions all the same? No, of course not. Again, not the point. That's not the question. Don't forget we get to add in partial constants. So the actual question is, are these three things all equal to each other? In the sense that, is there a function f that's equal to all three of these things? I get to choose whatever I might want to choose for these constants. Is there any way to choose these partial constants that makes all three of these the same? And so here I'm going to go. This is how I like to play this game now. I see an x squared y there and there. If all three lines are going to be the same, don't I need to have an x squared y here, where I clearly don't? A little discouraging until you remember I could just put that in here. Right? And now I've got x squared y in all three lines. And, we're making progress here. Okay, so similarly, I see, if I can get that to it right there, we go. Okay, I see an xz there and there, but there's no xz in here. But hey, xz could be that, right? It's a function of x and z. That's okay. So now all three of my lines have an xz term. And then lastly, let's see here, use blue. Minus yz squared. There's no minus yz squared there, but maybe this is minus yz squared. Perfectly allowed. There's no x's. That's allowed to be minus yz squared. And now check it out. All three of my lines, with those choices having been made, all three of my lines are exactly the same. They're all orange plus green plus blue. So that's what my anti-gradient is. Y'all all right? That all make sense? Okay. All right. So, this worked because there was an anti-gradient to find. I emphasize this is not going to defy reality. This is not going to produce an anti-gradient when we, in fact, already know that it doesn't exist. Right? So, case in point, let's look at this vector field. And let's entertain the question of finding its anti-gradient. Well, here's the thing. I can compute Green's operator. It's not 0. We already did that calculation. We know that Green's operator is not 0. There is no anti-gradient, therefore. So we're not going to be able to find it because there isn't one. Well, let's see how our method would work out then. Right? Keep in mind we've got this method, and I've got to take the the x antipartial of the first coordinate, and then the y antipartial of the second coordinate, and I'm going to need for both of these things to be equal to each other, and so thus begins the game. And what could I make that equal to, and what could I make this equal to? Is there any way that you can get clever about what this function of only y is, and what this function of only x is, and make these two green things equal to each other. And nope. You're going to lose that game. Right? It was just you spend 30 seconds on it, and I think you're going to give up fast. Right? It just can't be done. So the method will fail when the anti-gradient doesn't exist. Okay. Everybody all right? Okay, we are done with chapter 6. We'll be starting on chapter 7 on, what is this, Wednesday? Starting on Friday. All right. See y'all later. Have a good day. And as usual, stick around if I didn't check you off on attendance yet.